Now in this case, the frequency of the wave does not stay the same. Instead, we're using the frequency to encode a sound wave, or in this case, a plain old boring sine wave. So the resultant wave has a frequency that varies and isn't quite constant. We can see that when this wave is at a trough, the frequency is quite low and the wave is quite spread out. And when we're at a crest, the wave is very close together. The wavelength is very low and it's high frequency. But we still know what the carrier wave looked like. The carrier wave is what this wave would look like if it didn't have sound encoded in it. Now the amplitude of the wave doesn't change, which means that no matter how the amplitude changes due to outside source of interference or distance from the radio station, we'll still retain that modulation in frequency. It does mean, however, that we have to have a radio that's sensitive to more than just one frequency. It has to spread out over a short range, so it can still pick up the parts of the wave that are far away. Now, these waves are not quite as susceptible to interference. The reason for this is because if there's interference that changes the amplitude of the wave, it doesn't make a difference to us. We're not worried about the amplitude, only the frequency. The amplitude of the wave doesn't affect the message at all. So no matter how faint the message is, or no matter how many sources of radio interference are in the way, it won't affect our message unless they are of a similar frequency to our wave. In that case, we do in fact get a problem. We know that there are lots of different FM radio stations, and some of these have frequencies that are quite close together. The problem is that our radio receiver is sensitive to more than one frequency. So if we tune our radio to right in the middle of two radio stations, then we'll hear both at once. So there's a potential disadvantage of FM radio as compared to AM radio. It's easier to get two different radio stations playing at the same time. This is because the frequencies overlap as they vary. Is this wave a result of FM or AM encoding? Now what changes? Does the amplitude change? No, it stays the same. Does the frequency change? If you look carefully, then you can see that yes, it does. There are points here, here, and here where the frequency is much lower than the rest of the wave. So it's frequency modulation. The amplitude doesn't change. So sketch the decoded wave. We know that points with very low frequency, like these points here, will correspond to troughs in the decoded wave. In between these, there must be crests. We can see that directly in between the arrows I've drawn, the radio wave has a much higher frequency. So our wave will look something like this. Once again, we can see that the troughs match up with the arrows and the crests match up with the spots between them. So in order to decode an FM radio signal, we need something a little bit more complicated than just a transistor.